So in this talk, I would like to introduce you to my research, particularly in the area of my attempt to make program transformation, to make it a first-class citizen in the development process. I will give you, most of the time will be a very high-level brief overview of all the research directions and all my attempts towards a development process and development environment that treats software changes intelligently. For a couple of times, we will do a little bit of a deeper dive, but not too much, not too heavy into a couple of the tools, just to give a little bit more specific examples. One thing that I encourage students is to ask questions. I don't know if you are like me, but if I go into a presentation, I have a question, I'm not asking the question during the presentation, I wake up usually at 2 or 3 a.m., and my brain starts processing and keeps processing, I cannot find the solution, cannot find the answer, so I want you to all sleep well tonight, which means that you should all ask questions, and that's also good for me because it will save my voice. I want to get you guys to talk and me to get some breaks from time to time, so there will be another side benefit. Okay, so without any other detours, I just want to start in the talk, and I'm doing research in software engineering, and as a software engineering researcher, this is my view of what's happening today with code. This is the story. Our software, especially the one that is successful because it keeps changing. So we are reminded every day that our software keeps adding new features. Programmers keep fixing bugs. Yes, there are still bugs, lots of them left. Programmers, software engineers still have to change the software to support new hardware. So nowadays, everybody in the room has a multi-core parallel computing device in your pocket. If you have a smartphone, that's a multi-core device. If you have a laptop, my laptop here has 8 cores. These are all examples of changes that every successful software needs to go through. Nowadays, we are all transitioning from to a new user interface paradigm where all our software applications, the ones that are used by 99.9% of the end users out there, have a user interface and an experience that brings the users into the web sphere, into the web browser, brings the user into the mobile apps ecosystem. So underneath, yes, there is a lot of other software that stays somewhere on the server, but again, this is yet another example of software change that is imposed on us. But despite the fact that software is the changes at the heart of software development, the way how software engineers make changes today in their programs is very crude. I'll use Mike, a real developer working for the world's largest mercantile stock exchange company. It's somewhere in the Midwest, you can guess where probably. And I will use him as a prototype. He sits behind his keyboard and he makes large changes and continuously has to change the code base for his software, for his company. So recently he had to change a piece of code, and this required updating 100 other places in this large code base, which is about 4 million lines of code. Of course, he was using low-level text edits. He uses an IDE, but he still programs through low-level text edits, and he had to repeat the same change 100 times. It's bad because he never used all this change, but it's even worse because Carol, who is coworker, left on vacation for a couple of weeks. She came back, and she was trying to understand how is the code the way how it is today. She checked out the code using a version control system. They are using SVN, and some part of the code base runs also on Git. So they are using this standard state-of-the-practice version control systems, and all these version control systems, they represent changes at very low level, too low level. They represent changes as edits in files. So when Carol came back from the vacation, she was swamped with all these seemingly unrelated changes to hundreds of files. She was not able to understand why is the software the way how it is after she came back from vacation. So this is a story that repeats every day at every single software company out there. And this is one of the reasons that makes our software development ad hoc, error-prone, time-consuming, and very expensive. In fact, many studies found out that about 2/3 of the cost of software arise because of software evolution, because of the need to change existing running software. And there are some industrial surveys who put the cost much higher, even at 90%. So this is my view of, this is the way how I see software today. This is my view of tomorrow. I think if you ever want to see something in software equivalent to something that happened in the Industrial Revolution days, in the Industrial Revolution era, we'll have to lift up changes to a higher level of abstraction. So changes will have to become first-class citizens. So program transformations or changes becoming first-class when they become first-class transformations, we live in a world where most changes are carried through automated tools. So our friend Mike can script his change quickly, or maybe he can start partially editing his change in the IDE, and the development environment, the IDE starts inferring the rest of the change and will apply the rest of the change in the other 99 places of the code. When transformations become first class, our development environment will be able to learn from us, even if you are still using old tools, even if you are editing the code, the transformations are inferred. And this provides an orthogonal view of software, an alternate view of the software as a sequence, as a collection of program transformations. So our friend Carol, when she comes back from vacation, she's not looking at hundreds of files and looking at diffs that show hundreds of lines of changes scattered among hundreds of files, but she can see that here was a bug fix, here was a porting of the code from one version of a library to another, here is a fix of a security flaw, and so she can see changes at a much higher level of abstraction, which means that she'll be able to understand why is the code the way how it is today. So this is all good. How do we get there? So my research is driven by important questions. First, the first question is, what are even those changes that people make in practice? How do software engineers change their programs? Second, can we automate such changes? Like even if we partially automate them, this will still provide benefits, it will still provide productivity improvements. Third question is, can we represent programs as transformations? How, in this world, in this new vision, in this new era, how do we archive, how do we retrieve, how do we visualize programs in this new paradigm? The fourth question is, can we infer higher level meaning of changes, higher level transformations from lower level textual edits to the source code? So answering these questions, it's also challenging, it's interesting, it's worth pursuing, but also has very tremendous practical applications. So this is one slide where I want to tell people this is the way, my philosophy of doing research. So many people in software engineering employ empirical methods, control experiments, case studies. Now you build a tool and then you want to ask the question, did I build the tool right? But what I do in addition, I also go and use rigorously, I employ empirical methods also in the formative stage of the research. I ask the question, what is the right tool? Not only did we build the tool right, but what is the right tool? I also connect seemingly unrelated areas of computer science. So in my, you'll get a feeling of my research in the next few slides, but you'll see that I'm using techniques from traditional program analysis and compilers, and I'm combining them with HCI techniques and with data mining. And this is how I think this is how new, novel solutions can come to today's very hard problems in software engineering. I do a lot of tool development. With a lot of the research that we build is developed as tools that we put in the hands of software engineers. But I'm committed to go the extra step where I take these tools and put them into the hands of software engineers in the form of plugins for the Visual Studio or Eclipse or NetBeans or these other widely used development environments. So I'm committed to work with the developers of the development environments to transfer my research into the practice and to affect and to make a change in the lives of software practitioners. And I particularly like to, looking at specific problems, but I'm looking at how can we design, how can we solve a higher class of problems? So how can we come up with theories by looking at specific instances of a problem? How can we come up with theories and with solutions that solve the higher class of problems, solve a more generic problem than the one that we started from concretely? So for example, a lot of my work started from looking at refactorings, which is a specific kind of program changes, and now it's transitioning into looking at more generic transformations. So moving away from the refactoring paradigm, moving into the any sort of program transformation that people make out there in the wild. So how many people do even know what's a refactoring? Does anybody in the room knows what's a refactoring? So who knows what is refactoring? See that half of the hands raised. So let me give you a couple of examples of refactorings. If you're reading some code, and you encounter this method name, which is you really have absolutely no clue what it is. You finally read the code, the function, the implementation, the statements that make up that particular function or method. You realize, aha, this function, which is called foo bar, it's actually reverting a saved operation. So then you go and rename this function from foo bar or whatever cryptic name it had to do revert save operation. And then you have to go and find all the callers to this function or the code base and update all the callers to use the new name. So this is an example of a refactoring. In this case, you have not changed the behavior of the program is the same. The code still computes the same values as before. All that you did, you improve some aspect of the code. In this case, it's a non-functional aspect. In this case, you make the code easier to read. If the code is easier to read, then it's easier for you. But it's easier for somebody else who comes and has to maintain that code in the long run. Another example of a refactoring is you have a large program, and you have the same couple of lines of code, the same statements, who are copy-pasted in several parts in the code. Okay, what you can do, you take all these statements and extract them into another function and replace these statements with a call to this new function. So now you got rid, not only that you got rid a lot of duplication, but now you can, when it's time to go and make a change in your code, you just go and change the implementation of that single function. And because all these other callers call this one single function, they all use the new functionality, right? So how many of you have done a rename of a function or of a class or of a variable? See, many, many more hands. You see, you've all doing refactorings without even knowing that you've done refactorings. So a little bit of an overview of my research, and then we'll go into some specific examples of transformations and refactorings. So think about this as this is the wheel at the center, has a few spikes. One of them is in the area of automating. So I've been, along the years, I've been successfully automating changes from different domains, from the domain of how do we add parallelism to today's sequential programs? How do we upgrade existing code that uses obsolete versions of library APIs to bring the code, to make the code up to date so that we can use a newer version of a library API? How do we change spreadsheets, and these are used by end users, how do we change spreadsheets to make them easier to maintain and to read and to make them more efficient when they compute values? I've also been working in the area of inferring. How can we infer refactorings from lower level text edits? So if all that you've done, you use an IDE and you make some of these refactorings by hand, can we automatically infer that this is a refactoring? I've also been working in the area of testing, where I've been specifically addressing questions like, can we upgrade and can we automatically upgrade existing large test suites to bring them up to speed and to bring them up to date with the system under test? So if the system under test evolves, a lot of the assertions might become obsolete. How can we make them such that we refresh the test suites such that they run against today's new specs and new behaviors? I've also been working in the area of archiving and retrieving changes. So I developed the world's first version control system that is aware of refactorings and can show at the higher level of abstraction, can show the evolution of a code in terms of these refactorings. So you don't see that line 28 to line 45 in file a.java change, but you can see that this is a rename of a method, okay, this is a splitting of a large class into subclasses, or this is moving of a function from one module to another. So you see a higher level abstraction of the changes. You can, of course, you can always dig down into the lower level information if you ever want to find out how exactly it happened in the source code. And a lot of my work, as I said, has been driven by these empirical studies where we investigate how do software engineers change their programs. So today I will give you a sample of a couple of projects from the sphere of automating changes and then one from inferring changes, and we'll see how far we can get. Now, any questions so far? Okay, let's go into one of the examples of automation. So this is, imagine that at one extreme, you have a programmer who's using an editor, who's using a development environment to edit the code. The programmer is smart, has all this domain knowledge about what are the concepts the objects in the domain that he's trying to model. So if he's doing a business application, the programmer knows about accounts and transactions and all these other domain concepts. Right? But still the programmer is doing all these changes, is evolving today's large programs consisting of millions of lines of code. So he's still evolving, she's still evolving those programs using a primitive text editor. At the other end of the spectrum, you have compilers, which is probably one of the most successful stories in automation. So compilers, think about them as programs that change programs from one representation to another representation. And under the hood, they use very sophisticated program analysis, pointers, and reasoning about heap and memory, and data and control flow. So they do very sophisticated transformations of our code from one representation from the source to another representation which is executable. Okay, but there is only so much the compiler can do. Compiler doesn't know anything about the domain. Compiler cannot make your design more usable. Compiler cannot even make your code very performant. There are some kind of optimization for performance that compilers are good at, but there are many others that compilers are not good at. So compilers are notoriously bad at parallelism for adding transformations and making your code more performant when it comes to exploiting parallelism. So you see there's a big void here in the middle, and this is where my research fits in, where we take a version of the source code, we end up in another version of the code, combining both the smartness and the sophistication of compiler techniques and program analysis from compiler domain. So combining this with the insights and with the knowledge and with the input from the head of the programmer. So now my conjecture is that the programmer plus the sophistication, plus the help of the tool is much, much greater than either the tool alone or the programmer alone. So here it's a high-level overview of some transformations, interactive transformations that we have automated in the sphere of adding parallelism to today's sequential code. So we're automating refactorings from 3 domains, from the area of how do I make my code thread safe? I don't want to make it run faster yet. I just want to enable the code for later to add threads. So the second area where we've been successfully automating refactorings is from how do we add multi-threads? How do we add parallel resources in our code such that the code computes the result faster, so we get better throughput? And third is the area of we already have some code which is parallel. Can we make it more scalable? The code is parallel. It's running OK on a quad-core machine. How can we change the code to make it running equally faster when we go from a quad-core machine from a 4-core to a 8-core to a 16-core to a 32-core and so forth? So I just want to, as I said, this is, any of these bullets is a particular tool which is described in one of those papers. The main challenge is designing this sort of interactive program transformations is how do you put the power of sophisticated program analysis? We are using control data flow, using pointer analysis, constraint-based analysis. How do you make it such that it is interactive? How do you make it such that they produce errors which are usable and the programmer can take them and come up to a concrete actionable item based on the error that the program analysis detected in the source code? So that's one of the main challenges. And of course, how do you make all of this interactive? Now, these are some sophisticated program analysis that can take many hours to process a large code base. How do you take something that takes many hours and make it interactive such that the user can be engaged and continuously pose a question to the research tool, to the program analysis, and get back an answer in an interactive time? So just to give you a sense of a particular project, I would talk about one which makes use of lambdas. Lambdas are coming in all these languages. So a lambda expression looks something like this in most of the languages. It's an anonymous function that, in this case, we have a lambda expression that takes 2 arguments, x and y, and computes their sum. Okay, so it's anonymous. This is the hallmark of functional languages like ML and Haskell. All of these languages, make heavy use of these lambdas. These are anonymous functions that can be passed as arguments to other functions, or can be returned from other functions, right? And some of the languages, even object-oriented languages like Smalltalk and Python and JavaScript, had lambdas from the first time when they were released. But a lot of the other languages that people use today, they were retrofitted with lambda expressions. So C# and C++ have retrofitted lambda. think C++ it was a couple of years ago, and C# it was 3 or 4 years ago. And Java is the latest mainstream language that retrofits Lambda. So Java 8, which will be released next year in 2014, will have Lambda expressions. If you want to play with Lambdas in Java, you can even do right now, but you have to get a special preview, dev preview of the language and the tools. So why do people retrofit Lambdas in today's widely used programming languages? Is because they offer unobtrusive parallelism, and they fit very well with the way how you want to elegantly traverse over collections. So the question arises, well, I'm convinced that Lambdas are useful in all these other languages. Probably that's the reason why they're also retrofitted now in the mainstream languages. How can I take advantage of Lambdas in my code? My code is written in an imperative style. It's not written in functional style. So we developed a tool called Lambdaficator, which supports 2 refactorings. First refactoring converts an anonymous inner class to a Lambda expression in Java. And the second refactoring converts a for loop, the classical for loop, for I goes from 0 to whatever length, I++. It converts this style of computation to a functional style where I'm saying my collection.map.filter.reduce. So the advantage of the first refactoring is you get cleaner code, less clutter. The advantage of the second refactoring is this is unobtrusive parallelism and explicit semantics. It's easier to add. Mostly it's easier. You'll see it's much easier to add parallelism in your code. If the way how you are iterating over collections expressed with these functional operators, then it becomes almost trivial to take one of these sequential traversals and to turn it into a parallel traversal. So here is one example where we are iterating over a collection of blocks. So we have a collection of blocks. Our intent is to take all the blocks that are blue and to color them into red. So imagine that I have small children and they play with these blocks. This is 3D objects. They like to color them. So we have a for loop that does this thing for us. So if you're looking at this is a trivial code, right? If I want to parallelize this code, this is how I'm going to write it right now in Java. This is the way how I turn this sequential code into parallel code. So I have to add about 22 extra lines of code to just express that this thing runs in parallel. So that's bad. I don't want to ever look at this sort of code. So using Lambda expressions, you can take this code and turn it into this code, which runs in parallel and executes the same computation as before. So first, I convert my collections into a parallel stream, which gives me a parallel view of my blocks. And then I'm using 2 functional operators. I'm filtering the blocks that have color blue, and then I'm changing for those blocks that are passing this filter, I'm changing their color from blue to red. So essentially, I change my external iterator. So I'm iterating externally using a for loop. I change this style of iterating over my code with this stuff, which is called internal iteration, where now all the iteration happens inside of these functional operators. This is a functional filter, functional for each. And then everything else that is left to do is turn my sequential collection into a parallel collection. So this is more fun when you see it in practice, when you see it through a demo. And I have a demo here.
Anonymous inner classes, like the one shown here, are useful constructs, but the syntax is unnecessarily verbose. Lambda expressions provide a more concise replacement for anonymous inner classes, which only declare a single method. By the way, this code, along with other code samples, are taken from the Antler open source project. As you can see, Lambdaficator highlights valid refactoring sites, and by selecting the quick hint in the side panel, Lambdaficator performs the conversion automatically. As you can see, the new syntax is much more concise and easier to read. While this transformation may seem simple at first glance, our tool performs static analysis to ensure the transformation is performed safely. For example, in this method, the doPrivilege method is overloaded and can accept either a privileged action object or a privileged exception action object. When we perform the refactoring, Lambdaficator automatically adds a cast to the correct type. If this cast were not added, the resulting lambda would be ambiguous and a compilation error would result. In this next example, A variable declaration in the anonymous inner class hides or shadows a variable declared in the enclosing scope. While variable shadowing is legal in anonymous inner classes, Lambda expressions do not allow variable shadowing. Lambdificator will detect variable shadowing and automatically rename shadowing variables to avoid compilation errors. As you can see, a 1 was appended to the variable name to avoid any errors. The second refactoring highlights another feature of Java 8, internal iterators. Java 8 has added several methods to the collections API, which take a Lambda expression as an argument and enable functional operations over collections. Here are some examples of these operations, such as MapReduce, filter for each, and AnyMatch, to name just a few. Lambdificator can refactor existing external iterators, such as enhance for loops, to utilize these new internal iterators. In this example, we are calculating the total number of errors in a collection of rules. Although it may not be obvious, this code snippet is analogous to a filter map reduce operation. The if statement filters out elements. This function call maps a rule to its number of errors. And this compound assignment adds each error count to an accumulator. Lambdificator can automatically refactor this code to use functional operations. This example also shows that the types of the parameters in Lambda expressions can be omitted and can instead be inferred by the compiler. Without the aid of an automated tool, these refactorings are time-consuming and can introduce subtle bugs if done incorrectly. Lambdificator performs these refactorings quickly while preserving the original program behavior. In addition to this quick hint mode of operation, Lambdificator can also function in batch mode. You can select either a single file or even an entire project, and Lambdificator will generate a preview of all possible conversions in that selection. Even projects with hundreds of thousands of lines of code, such as Antler, can be scanned in a matter of seconds. This preview allows for fine-grained control over which conversion should take place, or it can simply refactor all possible conversions. Our Convert Anonymous Inner class to Lambda refactoring has already been accepted as an official patch to the NetBeans source code.
Okay, I want to stop here the demo. And go back into the slideshow. Okay, so this gave you a quick overview of what it feels to use one of these interactive refactorings and what's the user experience. Does it work? So we asked the same question ourselves, and also we had to convince the reviewers of our paper that this refactoring approach is effective. So we ran it on about 1 million lines of code from 10 open source projects, and we asked questions with respect to how applicable are the refactoring. So about 46% of these for loops that we showed before that were awkward, we were able to convert to functional style of iterating over loops. Refactorings improve the code quality. So for the first refactoring that converts this clutter, very verbose code, which uses anonymous inner class, we were able to reduce about 52% of the code size when we were using the Lambda expressions. Also, Lambdificator saves a lot of programmer effort. So if you were to apply the first refactoring, the one that converts anonymous inner class to Lambda expressions on one of these open source projects, on average, you'll end up changing about 412 lines of code per project. So this was done with the help of automation and interactive tools. It was done in 11 seconds. For the second refactoring, you'll end up changing about 1,300 source lines of code per project. And again, with the help of automation, we were able to perform all of these changes within 11 seconds. So, yeah.
So that top hole of yours, refactoring so widely applicable. So what does that 46%? What does that mean? That the other 54% were successfully refactored?
No, the other 54% didn't meet the refactoring preconditions. So one thing that I haven't talked about, all these refactorings have a lot of program analysis which is encoded under refactoring preconditions. So if the original code meets all these conditions, for example, if it doesn't shadows certain variables, if it doesn't use the this or the super or other variables from the super class, then we can take an anonymous signal class and make it into a lambda expression. So for this, all this means, it means that the code as it was written already, had met all those preconditions, and we were able to refactor the code. For the remaining 54% of the cases, you'll have to change the code dramatically to bring it into a shape which is amenable for refactoring. Yeah.
In the bottom bullets where you indicated that refactoring took 11 seconds, what would it have taken had it just been done by a program?
So I can only hypothesize what would be the amount of time. So so to change this, changing these lines of code, you change 400 lines of code. This is non-trivial change. You have to reason about side effects. You have to reason about control data flow. You have to reason about context of variables. So if you were able to edit the code with a speed of, I don't know, let's say, how much can you edit the code? How much can you change? What's the average speed of changing a line of code? If you are fast, it's what? It's
60 words a minute if you're fast.
60 words a minute. So let's say that this requires 30 seconds. Right? So 30 seconds times 412. Again, but I think this is way much more than 30 seconds, because this is not like monkey typing on the code. It's not like, oh my dear beloved, today I was running and jogging. But you have to think about the program and think about control and data flow. So we have not done, that will be an interesting study to do actually a controlled experiment where we measure how long it will take a human to make those changes. In other refactoring projects, we measured this, and we came up to about, sometimes we came up to about 800 productivity improvement if you compare the time that it took a human to do the change with the time that it took an interactive tool to do the change. So I expect it will be in the same, probably a couple of orders of magnitude productivity improvement. Any other questions here? No? Yes? Okay, was planning to talk about inferring transformations, but I'm thinking to skip this one. And I want to talk briefly about one area of work just to give you a little bit of diversity. So I'm not only working with source code, but also with spreadsheets that are used by end users. And spreadsheets have been around for, surprisingly, people have been using these grids and tables for about 4,000 years. How many people here can read Babylonian, ancient Babylonian? Anybody? No? Well, then this is a famous clay table from the ancient Babylonian. It shows the Pythagorean triplets. So first column and the second column are numbers, and then the third column is showing you what's the triplet, what's the third number of the. So if you remember from the Pythagoras, but people have knew about these Pythagorean triplets way before Pythagoras. So for those of you who don't read ancient Babylonian, there is a copy and paste error here. The result from line 8 is copied in the line 9, as you can clearly see here. So people have been making, copy and paste errors even in these primitive spreadsheets, thousands of years ago. Now, fast forwarding the history of humanity 4,000 years later, nowadays we are not using clay tables, we're using spreadsheets. And it's estimated that at least today there are at least 100 million professional people whose life and whose work and whose daily activities in their jobs depends on being able to work effectively and manipulate and process spreadsheets. So this is good because it means that if we can tap in this resource, we can have a huge impact. It's also good news because this means that being an order of magnitude more end-user programmers than classical traditional programmers, it means that also the rate of errors that they make in their code could be probably an order of magnitude larger than the rate of errors that we see in professional developed code. So we studied a corpus of 3,700 real-world spreadsheets. This was produced by the USIS, which is a corpus that Margaret has been putting together with some of her collaborators. We found that spreadsheets are riddled with the same problems that plague professional software. We found lots of duplication, lots of hard-coded constants scattered throughout their spreadsheets. So this decreases the maintainability. We found lots of redundant computation, which makes the spreadsheet slow and ineffective. And data from other research shows that the average lifespan of one of these spreadsheets it's about 5 years, and there are about 13 users, end users, who end up touching and evolving and maintaining that spreadsheet during its lifespan of 5 years. And smiles have masked errors that have cost the economy millions and billions of dollars. So this is something that came from one of the papers that Margaret wrote a few years ago. Here are a couple of examples. So TransAlta, it's a company, a Canadian company, that lost $24 million in 2003 due to a cut and paste error in Excel. This is a more recent one. Maybe that's why the government is shut down. But the Fed made the copy and paste error in their consumer credit report. And this was found, but could have led to a $4 billion loss. So I wonder if this is yet another reason why the government is shut down now. This was discovered in 2009, so that's how the crisis was avoided. So the government avoided losing $4 billion. So what do? We have refactoring. So we developed the world's first refactoring tools for end users, for those people working with Excel particularly. So supporting 7 refactorings, and they're implemented in a tool called Refbook, which is an interactive refactoring tool for developed as a plugin for Excel. And I want to skip over how it works, because I'm running out of time. Does it work? Yes, we've used series of experiments, control experiment, case study survey to find out if Refbook is effective. Yes, it's effective, it's reliable, makes the programmer productive, and refactorings are applicable. So I want to talk a little bit about the impact, practical impact of my research. As I said, I'm committed to go the extra mile and to move a lot of this research into the practice. So in the area of automating transformations, a lot of the work that we have done already ships with development environments like Eclipse and NetBeans. So for those of you who are still programming in Java, these are the dominant programming environments for Java programmers. They are used daily by millions of Java programmers. I have developed the world's first open source refactoring engine. So this was many years ago, 11, 12 years ago. In the area of inferring, again, this is something that I have skipped over, but our tools that infer refactorings from low-level text edits, they are already used in companies like Google and IBM, and they are already used at dozens of other research labs and by academics throughout the world. In the area of the testing, our work on generating tests for program transformation and for IDs is already part of the testing infrastructure at Sun, which is now Oracle, because Oracle bought Sun. So this is using the development infrastructure of the NetBeans IDE. The work that we have done in the sphere of understanding what are the changes people make to their code has already influenced the Java and the .NET official concurrent libraries. One of our websites, learnparallelism.net, which shows many thousands of examples of how people change their code to add parallelism in .NET applications, receives more than 30,000 visitors, and Microsoft now invited us to put a blog on the official MSDN on their blog post. So I think this will probably draw even more visitors to our website. Okay, a lot of collaborators, so there is nothing that I could do alone. There is a lot of work, and I'm especially grateful for collaborators. What I highlighted here is all the undergrads that have been involved in this research. So I have a passion of involving undergrads in research, and yes, undergrads can do research if you provide them the right infrastructure. There's a lot of master students and PhD students, and these are external collaborators from other institutions. Future work, I said I'm moving away, or not necessarily moving away from, I'm moving beyond refactorings into the sphere of program transformations, generic program transformations. So bug fixes, security improvements, improving performance, usability. So any other kinds of changes that people make in the world, we want to treat them essentially the same way how we've been treating refactories. We want to come up with development environments and with development processes that put changes at the heart of software development. So in the area of automation, we want to make it easier for people to custom script their own transformation so that they can apply their code changes on large code bases. In the area of composition, we want to come up with a science of composing transformation with a rich algebra with properties like commutativity, distributivity, conflict dependencies, where I can take a change, which is a bug fix that was applied on a code base, and I can take it and compose it with another bug fix that was applied on a different project, and I can come up with a novel with a new program transformation that I can apply on a yet completely different program. Right? So this is what it means for transformations to become first-class transformations when we can transform the transformations. I can manipulate and I can transform, I can revert the order of the transformation, I can compose them in unique and novel ways. Are you asking a question or you're just resting? Stretching, okay. Stretching is good. Inferring, so we want to be able to infer frequent unknown transformations. So far we've been using static analysis. I want to combine this with dynamic analysis. I also want to tap into the machine learning. So how can we infer unknown, previously unknown, using both trained and untrained classifiers. Archiving and retrieving, so there is a lot of work that needs to be done here on the sphere of visualization and integration with lots of techniques from HCI. In the area of understanding, again, there's a lot of user-centered research that we have to conduct to be able to come up with tools that the programmers can find usable and can use in their daily programming experiences. So this is a new thing that has been close to my heart for some time now. If you are looking, there's a new set of trends that are all converging, and they are putting lots of pressure on our software. So end users spend most of their times on one of these things. Like my wife probably spends 90% of her time on this. My parents-in-law and my parents probably spend 100% of their time on something like that. I cannot say that I cannot do PowerPoint, and I cannot edit the content of my lectures on one of those devices yet, but it's estimated that more and more people, so it's already true for a few years now that most of the people who buy computers, they don't buy them in the traditional form factor, like laptops and desktops, buy them in these mobile devices. Okay, so these are lots of new opportunities. I'm looking at these opportunities. Some people look at the problem and say, well, this is a problem, but whenever we have a problem, I'm looking at it as an opportunity. So this is some technological shift. All these mobile devices are going multi-core. The new generation of iPhones have 4 cores. They have lots of constraints on memory, CPU, bandwidth, battery usage. It's a different way how you program for the mobile device than the way how you program for a laptop, where you don't have to worry about what data structures you are using, or well, most people don't worry about it because memory is cheap and it's free, and CPU has been abandoned for many, many years. Here with the mobile devices, sometimes you are connected to the cloud, sometimes you are not. So all of this impose a new set of challenges and stretch the way how we develop software today. And as I said before, I'm looking at this as a set of opportunities. They might be encouraging some good old software engineering practices like encapsulation and modularization and being more clear and being much more clean the way how you write code. Because now you have to worry about a bunch of other things that you never have to worry on the laptop. So I'll be still working on interactive transformation, specifically targeting mobile devices. So here I have some examples. How do we adapt an existing app to use different display technologies? How do we split the functionality between the local device and the cloud? How do we split the data? How do we keep some data locally and access it locally versus keeping it on the cloud and making it consistent between all these other apps that are connected to the same data? And of course, as they said in the ad, there is an app for that. So there is a class for that teaches you how to do these things, where we are actually looking at some of these research topics. So this is the class that I'm teaching this term. So I want to conclude with a message that, as many philosophers have been telling us for thousands of years, change is the only guaranteed constant in this world. Everything has been revolving around the change. So if you ever want to foster a revolution in the software which is akin to the industrial revolution that happened a while ago, we have to take a step back and we have to raise the level of abstraction and the level of tools and the science that has to deal with those tools and changes from low-level text edits to higher-level transformations, to higher-level changes. And I've shown that at least for a very limited set of transformations, for refactorings, when we come up with interactive tools, we can make the programmer an Uber programmer more effective, and it's more powerful than just using manual approach alone. So many of our tools have already made it to official release of Eclipse and NetBeans IDEs, and this is your chance to make a big impact on the practice of software development. So you can make a difference too. It's just you need to be conscious. You need to be willing to pay the extra cost to move your research into practice. So I want to conclude with the message that today's brand new programs are tomorrow's legacy code, and this is what I'm going to continue to lead research, collaborate with others to come up with better ways to do software evolution in the long run.